guys will be live on YouTube, so get ready to be famous.
How many viewers?
A lot. So good morning, good afternoon, everyone. Today we have a new seminar lecture. Actually, today's lecture is divided into two presentations. It's different from the usual. It will be in the same format that is followed by the RBA, which is usually 20 minutes and questions for like 10 minutes. We have our first presentation will be given by Amir Parsa and Taghipour. They are PhD candidates in the University of Illinois at Chicago. And today they will be giving a presentation about real-time accident detection to improve time travel prediction. And our second presentation is by our own colleague Singhvi. He's also a PhD candidate, and he will be talking about aging. So please let's start with the first presentation.
Hello everyone, thanks for coming. I'm Homa, and today we're gonna present a part of a PhD research that me and Amir, my colleague, are working on. The title of the presentation is Real-Time Accident Detection to Improve the Travel Time Prediction. In this presentation, first I'm gonna start with an introduction about the topic, then I will talk about the whole framework for this study. After that, travel time prediction approach, which we use for this study, is gonna explain. And at the next part, Amir will gonna explain the accident detection problem that we solve, and finally a conclusion we presented. As we all know, that travel time information is really important in transportation studies because it could impact the road users' decisions, such as departure time, travel mode, route choice, or even when they want to cancel their trip, they need the information about the travel time. On the other side, the traffic operators need this information because they could manage and control the traffic to reduce the congestion and also increase the safety and efficiency. We expect to have a recurrent traffic pattern on the highways, but there are always some external factors that could affect this recurrent pattern. Some factors such as weather condition, road work, special events, or accidents are among these external factors. About the weather condition, we could predict the weather condition at least for a couple of hours in advance. Also, the roadworks and special events mainly are scheduled, and we could see their impact to predict the travel time for the future. But the accidents are not predictable, so we need to detect them as soon as possible when we want to use their impact in order to predict the travel time. Nowadays, the variable message signs that record the travel time on highways use some naive methods and use just limited sources of data. So their report might be a little not that accurate, or sometimes it is not reliable. So it needed to be improved. And for travel time prediction on highways, there are different methods. That the main challenge, I think, regarding these methods are finding a trade-off between the complexity and accuracy. Also, it is important to look at the different factors by using various data sources in the models. Another important issue is that it is important actually to see the dynamic nature of travel time when we are predicting it for the future. So in this study, we try to combine various data sources and use different data-driven techniques, including machine learning models, also considering the dynamic nature of travel time to come up with the best prediction. Here you could see the framework for this study. In this part, first we try to predict the travel time The first part was a literature review. After that, extracting data from different data sources. Then the data processing part, and after that, one of the challenging parts was to combining all these data sources that we had. After that, come up with the best model for estimating and then predicting the travel time. At the same time, we were doing the accident detection process by first processing the data, and the main challenge here was dealing with the imbalanced data, which is popular in accident studies. Then combining the data sources and then come up with the best model here. And the next step would be augmenting this model to the travel time prediction and use it at the end for dynamic travel time prediction, which is the next step of this study. Okay, for travel time prediction, the data sources that we used was from different sources. The first one and the main part was the loop detectors. From this data source, we had the count, occupancy, and the speed for every 20 seconds. This data set had lots of erroneous and missing points. We used some single and combined threshold to find the erroneous data points, and then using the temporal, spatial, and historical estimation, we tried to impute those data points. And here you could see the corridor that we started or studied on. It is the westbound of Eisenhower, a 12 mile from the westbound of Eisenhower, and these are the location of loop detectors that we have. Also here you could see the weekly pattern of average flow from the data, the loop detectors data. It is 1 week, it started from Monday, then Tuesday till Sunday, and you could see significantly on weekends we have different traffic pattern. So an important point here is that the speed that we have in loop detectors is the point mean speed, which is not that accurate. So we looked for another source to have a more accurate speed. The prop vehicle, which is provided by NRIX, uses millions of vehicles and trucks for the location and movement data. And in this data set, we had the harmonic average speed, flow speed, historical speed, travel time, and annual average traffic, daily traffic. It was available for every 5 minutes, and again, we did that data imputation part in this data set, and we had the variable of speed from this data source. And here you could see the average speed histogram from that data set. Another data that we used was the weather condition, which was available in different airport stations. And regarding the location of our corridor, the Midway airport was the closest station that we used. From that data set, we used the variable of surface temperature, also the weather condition, which was reported in 94 states, and we grouped that into 4 ordinal groups. The other data source was the accident occurrence. In this data set, we had the time of accident, geographical location, and severity of accident. From that data, we create 2 binary variables for previous links and next links of the accident from the moment of accident till 1 hour after that. Also, the accident severity variable used. From the roadwork data set, which was for the construction and maintenance on the highways, we had the start and end time, geographical location, severity of roadworks. Another binary variable is created here to show the effect of roadwork on the travel time. Also, the special event was the other source of data that we use. Scheduled stadium events or parades or road races was in this data set. We had the start and end time, location, and type of events. So we create another binary variable here. For example, if we had here the location of event, some of the links which were located in the past toward that event are considered 1 hour before starting the event, and the other links which were located from that event toward the other part of the city are considered 1 hour after the end of each event. The last source of data was the geometry data, which was number of lanes, number of entrances and exits, and lengths of each link which we used. So here, after extracting all the data from these data sources, we need to combine all of them to have one data set. Each of them has their own timestamp type and location type. Some of them was point-based, some of them was link-based. We combined all of them, and at the end we had a link-based data, and we aggregated all of them to 5 minutes. And here you could see the table of variables for our travel time prediction model. It started with time of day every 3 hours, then day of peaks, weather, occupancy, and count for each link, its previous link and next link, then location, geometry data, and those events and accidents data. Also, the models that we used for this study, we tried different machine learning methods, and here we brought two of the models that had the best result. The first one was the k-nearest neighbors. This model needs a large volume of data points that we had available. Also, the authenticity of the data is maintained. It looks at the historical data points to find the predicted value for a speed that we were looking for. Also, the random forest that works accurately and fast when we have a large amount of data, and it is robust to noisy data, or it is robust to overfitting. Also, it could manage a large number of variables that we had here. It creates the random decision trees, and the result would be the aggregation of each prediction from each decision tree. Using all these data sources and methods, we first selected randomly 80% of data to train the models, and then use the other 20% for evaluating the models. For the KNN model, the number of neighbors experimentally assigned as 4, and the random forest had 20 decision trees with the max depths of 30. Here you could see the result for the accuracy result for both models, which was developed for the prediction horizon 5 minutes till 60 minutes ahead. And you could see the green line, which is the result for the random forest model, had better result. At the moment of prediction, it could achieve the accuracy of 95%. And even after 1 hour, if it wants to predict the travel time 1 hour ahead, it could have the accuracy around 83 or 84%. The KNN model still had acceptable result, but you'd see the random forest is a little bit better. And here you could see on those figures, you could see the results of the true value versus the predicted value for KNN model, and here for the random forest model. For the moment of prediction, 5 minutes ahead, 10 minutes ahead, and 15 minutes ahead. You could see the best model would be when we are looking at the moment and in the random forest model, and when the prediction horizon increases, definitely the accuracy decreases. Also, for the random forest model, we analyze actually using the feature importance process, and here you could see the rank of variables which were important to predict the travel time for future. The first ones are the traffic-related variables. After that, AADT, temperature, and all of them. Amir will gonna explain the next part.
Thank you. Hello everyone, I'm Amir, and I'm gonna touch about the approaches and the models that we use to detect accidents in this study. So first of all, imagine we have a segment of a highway, and by a segment I mean the distance between 2 consecutive loop detectors. So we have 2 traffic conditions here. The first one is non-accident case, and the second one is accident case. You can see when we have non-accident case, the traffic condition is kind of similar across the road segment. And even by passage of time, I mean 1 minute from now, 2 minutes from now, this traffic condition would be similar to this one. But when we have accidents, that accident causes a shock wave, and traffic condition would change very fast. So you can see on the upstream of this segment, we have congestion, and in the downstream of this segment, we have free flow speed. And by passage of time, this congestion will get worse and worse. So based on what I said, we were thinking maybe we can use these traffic-related variables if we have some traffic variables from the beginning of this link and end of this link. Maybe we can use this data to capture this abrupt change in traffic condition, and based on that, we can detect accident in real time. So to do that, we use loop detector data. We have one loop detector at the upstream and one at the downstream of each link, which are collecting traffic data, including volume, occupancy, and speed, every 20 seconds. And for this study, I aggregated them into 1-minute intervals. Here, in the first step of our study for detecting accident, I started with Eisenhower, and as you can see here, in this part of Eisenhower, we had 23 loop detectors in such a way that the length of each link would be on average 0.6 mile. So we started with this scope, and in this scope, we only had 32 accident cases and several thousands of non-accident cases. So the data, as you can see, is highly imbalanced. And the objective of this part of our study was to train two powerful and popular machine learning techniques, models like support vector machine and probabilistic neural network, using imbalanced data. And the other objective was to determine the optimal number of minutes between 1 to 7 when the accident can be detected best after their occurrence. I mean, for each of these techniques, I trained 7 models. The first model uses the data from 4 minutes before accident time to 1 minute after accident time. The second model uses the data from 4 minutes to 2 minutes after accident time, all the way down to the model which uses the data from 4 minutes before accident time to 7 minutes after accident time. For training those models after doing feature engineering and generating our data, this is the final list of our data. In the first part of this table, you can see we have traffic-related variables. So for those traffic-related variables, we calculated temporal difference and spatial difference of these variables. For example, for speed, in downstream, we calculated difference between pairs of consecutive speed from 4 minutes before accident to n minutes after accident. Here I use n because n can vary from 1 to 7 based on what I've said. So we had, for the spatial difference, for example, for speed, we have the difference of speed between upstream and downstream for each of the timestamp that we had. So the story is the same for occupancy, and the next variable is a standard deviation. As I said earlier, our assumption was that when we have an accident, we have abrupt change in traffic variables. So we thought maybe by using standard deviation of this time series data, we can help our model to detect accident more accurately. I'm going to talk about this variable in the next slide in more detail. And the next two variables are weather condition and dummy peak hour variables for morning and evening times. So in this slide, you can see that we compared average of non-accident cases and accident cases for all of traffic variables at upstream and downstream. For example, for speed, in upstream, you can see the average of accident cases is higher than non-accident cases. This is exactly what we expected to see. And this pattern is kind of the same for all these variables, but we can see, for example, for speed at upstream, it's more obvious, it's more considerable than the volume in downstream. So the techniques that we used, the first one is synthetic minority oversampling technique to balance the data. This is a technique in which this technique takes 2 samples from the minority class and generate a random number between 0 and 1 and multiply the distance between these 2 samples by that number and put new synthetic data at that point and continue this procedure to the point that we have the balanced data. The number of accident and non-accident cases would be the same. So we use this technique. Actually, we compare this technique with the other variant of SMOT, and finally we come up with the regular SMOT to use in this study. And for training our models, we use support vector machine and probabilistic neural network. Finally, this is the result of our training the models. We use accuracy, detection rate, and false alarm rate. I think you know the definition for each of these measures. Here in this figure, you can see that we have the blue line is for PNN, and the red line is for support vector machine. And we have 7 points. These are the 7 models that we trained for each technique. So you can see that we can get the best result 5 minutes after accident time, because the most detection rate for both technique will happen at this point. Another thing that I want to say here is that in this type of models and studies, accuracy is not that important for us, because as you know, the data is imbalanced. So in the test data, we have several thousand of non-accident cases and only maybe 10 or 15 accident cases. So if we have a model which detect all the points as non-accident, like 0, this model will achieve 100% accuracy, and that's not a good model for us, because we want to detect those accidents. So we have to consider detection rate and false alarm rate, and as I said, the best result would be 5 minutes after accident time, and actually PNN outperform support vector machine. So in the next step of this study, we decided to improve our data. So we consider all Chicago highways, and now we have more accident cases. So for this part, again, the variable that we use is similar to the one that we used in the previous part. But this time we decided, actually the only difference is that we use the data from 5 minutes before accidents to 5 minutes after accident, because we got that result from our previous study, and we decided to just consider 5 minutes after accident time. So, but in this study, we decided to use more advanced techniques. Instead of regular machine learning techniques, we decided to use deep learning, which are better to work with sequential data. So at first, we again use SMOD to balance the data, and after that, we use LSTM and GRU to train our model. These two models are two RNN model, which are famous because they are performing well with sequential data. They have a concept of sequential memory, and as you can see here, we have hidden state that can pass information forward. So for example, if we have time series data in the last layer, we have some information from the first layer, second layer, and all the previous layers in this layer, and that's what we want to see, because this traffic data is time series, and we have that pattern in our data. The only problem of RNN models is that they are short memory, so the impact of the previous layers is much more than the earlier layer. But the structure of LSTM and GRU overcome this problem. So based on their unique structure, they have some gates, so they remove some unimportant information and just keep some important information and move that forward. So we use these two models, and here you can see the result of training these models. These are the parameters of our models. This is the result of confusion matrix of this model, and finally we use that to draw ROC curve here. And you can see both model performs well. The area under curve is about 0.85. So both model the result of both model was very satisfying for us. So let me conclude this presentation with several points. First one is that, as Homa said, comparison of random forest and KNN models showed a good performance of predicting travel time. Random forest performed a little better than KNN. Traffic-related variables, especially occupancy, was effective in short-term travel time prediction. Fusion of several traffic data and other sources of data, as Homa explained, helped us to predict more accurately. And some other data like accident, especially when a road works, we found that are important variable that we have to consider in travel time prediction. Also in accident detection, we find out a smooth we compare that with the other techniques, and we realize that a smooth is really good to balance the imbalanced data of accident data. And finally, after training several machine learning techniques, we come up with the result that RNN models, I mean the special type of them like LSTM and GRU, performed very, very well for this study and for this data. This is the last slide, and we would be happy to take any question, any comments.
So I have two questions. So first, whenever you say like accident detection, what do you exactly mean by accident detection? Is it you're predicting when there is an accident will happen, or what exactly are you doing?
So we have, for example, we have, as I said, we have some loop detectors in the highway, and imagine there's an accident in that highway.
Yes.
After that accident occurs, there is a shock wave, and the traffic condition before that, in the location before that accident and after that accident will change. So when we have accident at this moment, 2 minutes from now, 3 minutes from now, we will see change in these values that loop detectors are collecting.
Yes.
So based on that, we can say, okay, we know that at that location, by that location, it means that interval between those two loop detectors, we have an accident based on the model that we train. This is the concept.
Okay, so as a follow-up, so whenever you say what you're trying to do here is to incorporate it at the end of the day in a travel time prediction model. So first, how in order to do that, now you'll know like after 2 minutes you have like you'll have a queue or you'll have a problem there.
Yeah.
First, how will you be linked to travel time? Because you need then to also predict the accident to be able to predict how much problem you'll have after that. This is one. And also in your neural network, whenever you are creating this, how do you take into account like the road geometry? Because like there is a lot of highway and expressway that they have an additional lane in case there is an accident, so they move it quickly. In some other cases, you just have like 3 lanes maybe with no additional lane for accidents, so you'll definitely have a queue. So how do you take this also into account whenever you're taking the impact of having an accident on the travel time?
Yeah, sure. For the first question, the first solution that we were thinking about, and it was a kind of naive, but the first solution could be when we use this accident model, even if it can detect accident 2 minutes after their occurrence, we can use the output of this model as an input of the other model that we trained for travel time prediction. If you remember, in the table of variables for that model, we had is accident, which take 1 or 0. So if we have an accident, we can put that in that model, and based on that, the travel time which will be predicted will be different.
For example, when we are predicting the travel time for a corridor with, for example, 10 links, we start from here and predict. That would be the dynamic prediction which we are using in the next step. We are predicting the travel time for the first link for now. The next link, for example, for 5 minutes from now. The next link 10 minutes from now. And when we know, for example, we have an accident here and it was 2 minutes ago, that's fine. But when we are predicting the whole corridor travel time, we know that in the future we're gonna have that effect. And when we are predicting the whole corridor travel time, we could see its impact for the future, but not for now. And about the prediction of accident that you said, okay, it is not possible, never, that you could predict. There are some travel time, accident prediction studies, but they're just about probability of the accident occurrence, not exactly, never you could say.
Exact time and location
Yeah,
of that
so
accident.
the best case is detect it as soon as possible and see its impact on the travel time in the future.
And regarding your second question, do you want
Yeah,
to
about the geometry.
Yeah, about the geometry, that's a great point that you mentioned. For the first part of our project, we consider Eisenhower, we observed all part of Eisenhower, and we saw in all part it has 2 or 3 lanes, and the geometry is kind of similar. If you remember, it was a straight line. But in the second part, yeah, your comment is completely correct, and we have to observe that. our idea was that when we input as much as possible data in the model will train these patterns of traffic, the accident, pattern of traffic after accident. That might happen. For example, we have an accident, they pull over, and there isn't any queue. So that's the part of that. For example, the accuracy, the detection rate of our model is not, for example, 100%. These are the parts that we miss in our model.
But in travel time prediction, we had the geometry variables. We had the number of lanes, lengths of lanes, number of entrances on each link, and yeah, we could see that if, for example, sometimes you had a link with a higher number of lanes, maybe the accident will be ended sooner than the other parts.
Thank you.
Well, thank you very much for the presentation. For the first part, well, the travel time prediction is like a continuous thing that you would like to find out at the end, but then you use some sort of like classification methods to come up with the travel time.
No. And that all of those methods we use the regressor type of models. All of them are type of regression, not the classification. Yeah, because we are predicting at first the average speed, which is a continuous variable, and if we use, for example, on the random forest, we use the random forest regressor in the
Okay, so then
all of them are, in the first part, all of them are regressions. The second part for the accident prediction are the classification.
So then, for example, using KNN, you would just get the nearest one and then you would regress from that, you mean?
The result that we give from the model is a value of speed, which is, for example, for the random forest, it is the value of speed that was predicted from different trees, and the result that we see is the aggregated average of all those variables.
For the KNN is the same, taking average of the nearest point, speed of the nearest point, and that's the output of the model. Okay.
I think we'll just take one more question, and then we'll move to...
Thanks for the nice presentation. I would like to ask if, for example, you could label some extreme cases. For example, if you have a pileup, I hope nothing of this happens. If you have a pileup in a highway, like 30 cars have an accident, it was actually... No, I read about this in Ontario yesterday. So, for example, this case would be very costly, let's say, to the model of time travel, but at the same time, maybe in the classification, if it is an extreme point and it wasn't detected, it would be hard to extrapolate on. So, would you do that for some extreme case?
The nature of this accidents, they are happening rarely. So, but even if that happens, I'm thinking, for example, it started from one link. Okay, so at first, 2 minutes or 3 minutes after occurrence of that accident, our model should detect that accident because we have free flow speed after that, the location after that accident location, and we have some congestion in the loop detector in upstream of that accident location. But the traffic pattern in the previous lens would be different from those that we can use for detecting accidents. For example, on both upstream and downstream of all previous links, we have congestion. And that's not the pattern that our model realized it's an accident. You know what I'm saying? So based on that, I expect our model detect that accident, for example, 3 or 4 minutes after accident time at that exact link location. Did I answer your question?
Yeah. Thank you again.
Start?
Yeah, of course.
Okay. Good afternoon, everyone. So today I'll be presenting a work which we submitted in TRB 2020, and the work is about effect of binder source on the asphalt concrete's flexibility over long term. And before I start, I would like to acknowledge the co-authors here. Singhvi Zhu, who's actually the corresponding author for this work, and unfortunately he's not here because he has a class to attend, and that's why I'm here. And Uthman, Dr. Ozer, and Professor Alkar. So the outline of the presentation would be to introduce you why we are doing this, the objective of this study, what materials and methodology was used, and to share the results of how effective binder source is on overall mixture flexibility, and some key findings. So, just to have an idea about how asphalt concrete is subjected to variety of environmental conditions, and on top of that, you have traffic moving onto it. So with time, the material gets deteriorated. Now, there can be different forms of distresses happening onto the asphalt concrete, but with aging, one of the most prominent distresses is cracking, which aggravates with aging. Now, the binder present in these asphalt concrete mixes have a tendency of aging. Not all binders age the same way. And this comes from that the parent crude used to get that binder is not necessarily the same. Also, the refinery process which has been incorporated to get those binders might be different. Furthermore, you might have to do some formulations by the time you get the binder out of terminal. So what you get out of the terminal can have a binder with a similar performance grade as per Superpave specifications, but can have distinct long-term performance in terms of cracking as well as rutting. So the idea is to detect these changes happening in the binder source, and can we predict these changes to the long-term performance of our mixtures. So just to bring you back to 2015, where Illinois Flexibility Index test was developed to predict asphalt mixtures cracking, and this test, when was developed for an unaged specimen. But with aging, we know that our mixture is more susceptible and more prone to cracking, and that's where the long-term aging protocol for IFIT was developed in 2018 as part of our 27175 project. The long-term aging protocol incorporated a compacted IFIT specimen to be aged in a forced draft oven for 3 days at 95 degrees Celsius. And this was the outcome of this study, which is relating the long-term performance of mixtures in terms of cracking. So with that idea, the effect of binder source will be studied in this project, to evaluate its long-term cracking performance, and to develop some sort of correlation between the rheological properties of the laboratory aged binders to that of the flexibility of the long-term aged asphalt concrete specimens. So for this study, a specific set of materials were used. So 7 mixtures, asphalt concrete mixtures, were designed at our lab, and they were divided into 3 basic groups. And these groups were differentiated based on the amount of recycle they had. So the first group was having no recycled content, the second group had around 20% of ABR coming from the wrap, and the third group had 26% of the ABR coming from wrap. And just to make it clear, we used only wrap as a recycled source. And the wrap used in all these mixtures, all the 3, 4, 5, and 6, 7 mixtures, the last 5 mixtures were coming from the same source. Also to note, all these mixtures had a similar mix design with end design of 70 gyrations, nominal maximum aggregate size of 9.5 millimeter, with a VMA, target VMA of 15.2, and an total asphalt content of 6.4%. All these mixtures, furthermore, the only difference between mix 1 and mix 2 was the binder source, to see the effect of binder source. And in the experimental group 2, again, the binder sources were different, but they were all same grade. And similarly for group 3, we had similar binder types, but the sources were different. Just to note that mix 7 had a binder of 5828, but had recycled engine oil bottoms. And just to give you a heads up on REOP, it has been shown in the study that presence of REOP does have a detrimental effect on asphalt mixtures cracking.
Just a clarification.
Yes.
So here, what's the idea of changing the source and also adding EOP?
So
How
this,
do you know the difference? Where is it coming from? Is it coming from the source or from the real?
so this binder was developed from a parent 64-22 binder, which is not here, but the final binder was 5828, but it had re-op. That's the idea.
So
So it is a 5828, but made out of a re-op, whereas whereas if you see the other binders which are named as A, B, or C, they didn't have re-op, but they can have obtained from different blending at the terminal.
And the D is a different source from A, or is
Yes, it is a different binder, different source from A. So the idea, the experiment plan followed was to evaluate the mixes for Illinois Flexibility Index and Illinois Flexibility Index at unaged and aged conditions, whereas the binders were tested at different aging conditions, including PAV and double PAV, and were tested for BBR test and time, temperature, frequency, sweep, and eventually they were related to the IFIT parameters. So the aging methods for mixture aging, long-term aging protocol, as I mentioned, was 3-day 95C developed as part of R29.75 was used, and for binder aging, 20-hour PAV and 40-hour PAV were used to represent long-term and extra long-term aging respectively. So just to give you an overview of what an IFIT test is, it's a 3-point bending test which is applied on a notched semicircular asphalt concrete specimen. The thickness of the specimen is 50 millimeters and is conducted at 25 degrees Celsius with a loading rate of 50 millimeters per minute. The test gives an index called flexibility index, which gives a measure of asphalt concrete's cracking susceptibility. So if you have a higher flexibility index, you expect your material to be more flexible, which means it's better in resisting cracking. Whereas for binder testing, frequency sweep testing was used. So the sample size was 8 millimeter dia with a 2 millimeter height and was tested for 15, 25 and 35 degrees Celsius over a range of frequencies varying from 0.1 to 20 Hertz at 2 different aging conditions. The parameters obtained out of this testing were Glover rho, which is again an indicator of cracking susceptibility of binders, crossover modulus and R value, and I'll discuss in the results how these numbers changes with aging. Another test for binder characterization was used was BBR, and the two parameters obtained out of this test were M value, which is kind of indicating the relaxation properties of the binder, and delta TC. Delta TC, it's a well-known parameter which is basically a difference of the temperatures or PG coming out of from the stiffness criteria subtracted by the PG coming out of the M value criteria. So let's get on to the results. So when all the 7 mixes were tested for IFIT, they were tested for again unaged and 3-day 95C, which is a long-term protocol for IFIT, and we see that within these groups, the group 1 represents same mix, but the only difference is the binder source. And you see that there is a difference in the IFIT values both before age, both at the unaged condition and at the long-term age condition. When we go to the second set, again we see that the differences in the flexibility index values both at unaged condition and at age conditions were observed, even though the mixes were the same mix with same amount of recycled content. The only difference was the binder source. So IFIT was able to pick up both at unaged and aged conditions the differences in the binder source. Interestingly to see the third set where we intentionally put a re-op based binder, and we know that the effect of re-op impacts the cracking resistance. We couldn't see a detrimental effect if we look at the unaged condition of the IFIT. We saw that adding re-op was kind of showing a better IFIT for unaged condition. But as we aged it over long term, we started to see the detrimental effect of re-op coming into picture. So that was something interesting which was picked up by the long-term aging protocol of IFIT. Now if we look at the binder testing results, if you look at the Glover rho parameter, again, just to give you an idea about how Glover rho works, the higher the Glover rho, you have increased chances of cracking susceptibility and you expect Fi to decrease. So if you see the results, this is what you will expect. That the group with the first set you see that if there's a decrease in Fi, there is an increase in GR, which makes sense. Again, if you look at the second set, the trends were pretty much what we were expecting. That with in a decreasing Fi, you have an increase in global rho because you have higher susceptibility of cracking. However, at the PAV condition, when we saw the last set, which was the third set, the effect of reop was kind of not following the trend. It was showing that even though the cracking susceptibility over long-term aging, and just to clarify this, flexibility index is for the long term. So with long term, the reop binder had a decline in the flexibility index, but which was not picked up by the global rho at PAV. Again, if you look at the 2 PAV, we saw the similar variation. With the increasing global rho, you see a decreasing Fi for 2 sets, but for the third set, which had a reop, again the global rho was not able to pick up the detrimental effect caused by reop. When we look at the crossover modulus, it's another parameter which is calculated based on the frequency sweep test. Again, for the crossover modulus, if you have a lower crossover modulus, which means that you have an increased cracking susceptibility, and you expect the Fi to decrease. And if you see the trends were pretty much consistent for PAV condition. When you look at 2 PAV also, you see the similar trends for all 3 groups, which was consistent with our finding from long-term aged IFIT. R value, again, it's a parameter coming out from the frequency sweep, and typically the higher R value indicates increased cracking susceptibility. So again, this is similar to global rho trends, and you see that the trends are kind of followed in all of the cases in PAV aging condition as well as over the long-term aging conditions. You see the similar trends. However, for 2 PAV, it's inconclusive to say it's increasing, but there was a slight increase. You can say it's pretty much the same too. But in PAV, you definitely see that the R value kind of increases, and which means the flexibility is expected to decrease. Which means that these rheological parameters coming out from frequency sweep does have some relationship to the long-term IFIT. If you look at the BBR value, M value indicates the relaxation property of the binder. So if you have a lower M value, you expect higher cracking susceptibility. And if there's a higher cracking, you expect a lower Fi. And that's what you see in 2 groups, group 1 and group 2 of the mixes. But when you look at the reop mix, again, there was a counterintuitive observation, which means that even though your M value increases, the material is not able to relax, and it's having a lower flexibility index. But at 2 PAV, after prolonged aging, you started to see that yes, M value also kind of dictating how the flexibility index is changing. So PAV method, at PAV aging, M value was not able to detect, but with prolonged aging, you started to see that effect of reop kicks in. Another parameter out of delta BBR testing is delta TC, which is widely used to represent cracking. And if you see again here, at the PAV condition, the trends were followed for 2 sets of mixes, but for the third set, which had reop, you don't see the trend following with IFIT. And the reason being, probably the reops didn't the effect of reop didn't start kicked in. And when you look at the prolonged aging, that is 2 PAV, you started to see again it follows the trend. So for BBR testing, both M value and delta TC, you saw the trends correlating to IFIT at 2 PAV. So just to summarize the findings, long-term aging protocol of IFIT for IFIT was able to screen mixes with different binder sources, and the effect was evident both on unaged and long-term aged conditions. However, with the long-term aged conditions, especially the binders modified with reop, the effect of reop was more visible. If you look into the rheological properties of the binders which were used in this study, parameters like crossover modulus and R value at both PAV and 2 PAV kind of follows what IFIT predicts in terms of cracking susceptibility, while the BBR testing parameters like M value and delta TC, only 2 PAV condition is able to detect the effect of impact of cracking happening onto the mixes. However, global rho is again a parameter which is used to predict cracking performance, was holding good for 2 set of mixes out of the 3 mixture sets, and hence need more verification and investigation to see what happened, why it's not picking up. Even at PAV and 2 PAV, it's not following the trend as IFIT is following. So with that, I would like to acknowledge IDOT and the binder suppliers who provided the binders at the time of project R27-175, and the research engineers, students and staff at ICT. With that, I open the floor for questions.
Yeah. So thanks, Puneet. It's a great presentation, and you really did a nice job delivering it. It was very good. So I have 2 questions. First, all of these binders are not polymer modified, correct?
Yes,
Unmodified.
they're not polymer.
So I think this will answer your question about Glover Rowe. Like Glover Rowe, in Glover's original work, he says this parameter is very good for unmodified binder, and it totally falls apart when you use modified binders. And at that time, he was studying pretty much exclusively SBS modified because that's what was popular in Texas. The reason for that, I think, is because it's based on a Maxwell model. I don't know how much Riyab you're using, but probably...
For this binder, I think, if I'm not wrong, it was around 9% Riyab.
I was going to say probably to bump it
Bump it
PG
down.
grade down,
Yeah.
you need about 10% Riyab.
Yes.
So probably you're using a pretty high amount of Riyab. So this all is based on Maxwell model actually. And once you add Riyabs, that Maxwell model cannot model your binder's behavior. So I think this is why the Glover-Rowe parameter, the whole idea is to derive ductility from the Maxwell model, and I think this is why it's not holding up for polymer modified and for this unmodified or Riyab modified binder.
Thank you for the comment.
So that's the first thing. Sorry, it's more of a comment, and
Yeah.
the question was about that. Was about this SBS modified or
Yes.
polymer modified.
Yeah.
The second question about this delta T sub C. Can you go back to that slide?
You want to see the...
Oh yeah, actually, no, the last one, the 2 PAV.
Yeah.
So, my understanding, it's hard to see what you have on the axis there, the delta T sub C. Is this increasing delta T sub C is down?
It's decreasing, so it's 0, -5, -10,
Okay, I
-15,
understand. So-
and -20.
Increasing absolute value of delta T sub C is down.
Yes, yes.
Yeah. So,
So it gets worse. It goes to almost -10,
yeah,
and it started with almost positive. So the drop of delta TC was significant and was evident at 2 PAV, was not visible at the PAV aging condition.
So actually, I'm shocked that almost nothing is passing, like the proposed spec, right, in 2 PAV, almost none of these PG binders are passing, even without the Riyab, but actually, like,
Something is close to like -5, some
Yeah.
binders are close to -5, some
I mean,
are
more than
like
half
low.
of your PG binders are failing, like the proposed spec, and even close to -5
Yeah.
could be under, because there's a high error,
Yes.
compounding error.
Yes.
So actually, even those ones that are like -5.
Yeah, they are on the borderline for
Yeah.
2 PAV.
So actually, you could be failing all but one PG binder in this delta T sub C.
We have seen like now another thing is for like it has been initially the criteria used for PAV was -5, but now it has been moved to 2 PAV,
Right.
and I think different states are adopting different criteria. For Illinois, I think we don't have a study where we have said like, okay, is it -5 to go or is it minus, for PAV or 2 PAV? So I think we are still exploring that, but other states, you're right, they have adopted, I think, mostly, and I think Javier can add on to that. And -5 is the most common at 20-hour PAV, right? Is the criteria.
Correct.
And I think NCAT's proposing -5 at 40 hour now. So this is
Yes, that's the
yeah.
40 hour.
for the 40-hour view. So this is something to consider. Like,
Yes,
if
yes.
this criteria, if it's only
Then-
valid based on your local materials,
Yes.
then actually this is a problem for implementation too.
Yeah.
So it's something to think about too. But
Yeah, that's a valid point.
We would, to consider that, we would also have to have the testing temperature there. Are we all the same, tested at the same temperature for that delta to see?
Yes.
Okay, so
Yeah.
then it's a fair comparison.
Other questions? Do you want to ask? Yeah, ask.
Yeah, but you can go for it.
So here, whenever you're, I have one comment and one question. So here, whenever you talk about Riyab, it goes back to my previous question. So everything between mix and 6 and 7,
Mix 6 and 7.
In
yes.
addition, that one has reop and the other one does not have. They are also from different sources.
Yeah, they are from different sources too.
So why are the results always blamed on reop, the existence of reop? Not blamed, but I mean the explanation is being
Yeah.
dropped on reop, not also taking into account.
I think you have a valid question. So the question again, I repeat, is that the binder used in mix 6 and mix 7, the base binder might be different. And again, as I said, mix 6 didn't encounter any modification. So it was coming from the terminal. So it might have a different source, but it has been known that if you add reop does have a major impact on the properties of the binder. Even though, like even though if they have different source, 9% of reop is too much to cause that detrimental effect. But again, you're right. Putting everything on reop is not true, but reop does
Especially
have
that
an
the,
impact.
mix 1 and 2 and 5, 3 and 4 tells you that there is definitely an impact coming from the source.
Yes.
If they were showing me that there is no impact, then I would say yeah, it's all from reop. But there is. And my other question is, if you go back to the slide where you were showing IFIT, the result age and unaged.
Mm-hmm.
Can you please go back to the slide?
Back here. Sorry.
Yeah, this one. I'm interested in seeing whenever you look at age and unaged, you see that there is the exact same trend, right?
Yes.
It's very close to unaged or
Yes.
aged. Do we always see that? Because I'm not sure in the field if it's really,
The thing
why
is,
do we study unaged if it's aging properties, if it gives the same thing as unaged? I'm not very familiar with the topic, but it's interesting to see if we're seeing the same trend, then why do we need to age it?
so one thing is, in field we have different types of binders. They can be polymer modified binders too. So the way polymer modified binders will behave might be different. So these are not polymer modified binders. So that's why we probably kind of see the trends are pretty much same at unaged to that of aged.
So it's fair to say that if it's there is no polymer, we don't need to age the specimen. We can test it on age.
I won't say that. I won't say that. But look, because this is based on the lab mixes we prepared in our lab, and they have the same closed mix designs. And if you go into the field now, if you're comparing different mixes, then those mixes can have difference in gradation, binder type being used, whereas these all mixes, they are all coming from the same mix
Yeah,
design.
I'm not criticizing the way, but maybe what I'm questioning is the way that we age it in the first
Yeah.
place. Is it really showing what is happening? Because I don't expect mixes to perform the same way if they are aged. No, it's to have the same trends.
Yeah, for example,
Especially for such like 7 mixes.
so for example, like if you look here, like here you see the difference coming, right? So even though that's what the point is, like these two mixes at unaged condition, here you can say that they're close to each other, they're all passing the criteria. But as you go for long-term aging, you see this differences coming into picture. So not always these trends will be the same. Like for example, here also, if you have noted mix 5, you start with a higher IFIT, but then you have a little bit lower from the one which is at mix 3. Now again, these two binders, their sources are different, and that's what the idea is, that unaged binders might not.
But
unaged
originally,
binders-
are they statistically different?
yeah, statistically they are not different. They're close to each other. But then the idea is, like, there can be binders, the way you are modifying can change the long-term aged IFIT values. And that's why you need to look at the long-term age too. And that's why in the study 175, we have a protocol for long-term, as well as we want the initial FIs to be, a certain criteria. So both of them are kind of important.
Thank you.
Sorry, just
Yeah.
one more thing related to that. These are aged, the actual specimens, semicircular specimens are aged, correct?
Yes.
So I wonder if you see a difference, and maybe you guys explored this in a previous project. Do you think you'd see a difference if you age the loose mix and then compact the aged material?
So, there are differences, but the trends were pretty similar when we did the initial set of mixes.
Okay.
So with loose mixes, you tend to get faster aging typically.
Right, exactly.
But then the trends were pretty much similar, and based on the TRP discussion, they came up with, okay, we are going to use the semicircular specimens directly compacted and then age it because of several other reasons,
Sure,
like
yeah.
practicality and also like the changes, the absorption changes when you put the mixes in, loose mixes in.
So on this same slide, you say the objective, or what you're saying is that IFIT is able to distinguish from different sources. But then you said that these were statistically the same, like they weren't found to be statistically different.
Yes, I mean, so for example, like if you group 1 to compare to group 2, they were statistically different.
And group 1 is the same binder source, and group 2 is another binder source.
Group 1 had 2 different binder sources.
Okay.
So within them also, within these also, there were differences statistically between these.
Okay.
And if you look at group 2, here, they were pretty close to each other except mix 4. So you can say mix 3 and mix 5 were close to each other statistically, but mix 4 wasn't. So it was able to see the differences. Now, for some mixes, the difference was statistically significant. For some mixes, it wasn't. That's the idea. And since they are all same grade, and if they're not changed, and I don't know how they were formulated at the first place. So if they're not formulated like, significantly different from the other, then probably they might fall around the similar numbers. This is what we are seeing here. So again, how they are formulated, it depends on that, on how the formulation was done. Whether this 5828 was obtained by mixing some sort of oil to 6422 or some sort of other petroleum-based oil to 6422, that will dictate how it will affect or how it will change with aging.
I have some questions about the binder parameters you guys were using.
Which ones?
For the R value,
Yes.
did you fix the glassy modulus?
Yes, in this study we fixed the classic.
So do you think R value gives you something that crossover modulus doesn't? Can you see something from R value that you cannot see from crossover modulus?
I think for R value, again, the idea is we use a fixed value, which has been always argued that whether it's the same value or it's a different value, since it's the parameter which we get out of the frequency sweep, we used it. But crossover modulus is a parameter that can be obtained directly from running a test, and that's why I think crossover modulus is much more confident. We are more confident in crossover modulus. But this is what we found from assuming that the glassy modulus is same. It's a valid point. Like the glassy modulus, if it's different, then assuming that might result in a different trend.
And did you guys look at, or is it possible to now look at the phase angles?
That's a very good point. We haven't done that, but we have the data and we are planning to look into the phase angle, because in another study we saw that the phase angle, the change of phase angle does have an impact with aging, and you can see how different binders can be differentiated using phase angle, and we probably will look into that too. Yeah, but in this study we haven't. Since we have the data, we can always go back and that's a good point.
Okay, thank you so much. You're amazing. The way that you listen. I love the way that you're not just really communicating, but you're